the next talk. The next speaker is going to be Dr. Getahun and his team. And the project is about the how to assess the digital infrastructure. I make the introduction short to give more time to the speakers, and hopefully at the end we're going to be having some time for questions. Dr. Getahun, the stage is yours.
Thank you. So, our project is about rural road infrastructure assessment and enhancement for autonomous vehicle deployment. This is a joint project between North Carolina A&T and University of Georgia. So my name is Tesfamichael from the North Carolina A&T side, and Dr. Handong will join me later from the University of Georgia side. Okay, so these are just the brief outline of the presentation. I will provide a very brief introduction about the project and the motivation behind it, and then I will show you the main objectives of the project, and then I'll go in detail about the assessment framework that we developed for road assessment, and then I will discuss the results we achieved, and we finished the presentation with some concluding remarks and some brief limitation discussions. Okay, so the motivation behind this work is that there is a question that why do we need rural infrastructure assessment? So it turns out the AV systems are designed and they are validated under some specific infrastructure assumptions. However, when it comes to rural areas, this assumption might be violated, and this can lead to very poor AV performance. So then this kind of assessment obviously helps to some extent. So because it helps us identify where the AVs can operate safely today in the existing road infrastructure. It also helps identify the infrastructure limitations that can affect performance. And it can also help us prioritize what kind of infrastructure improvement that one needs to do to bring the infrastructure to the level that's expected, that the AV expects. Okay, so to give you very brief ideas about what the AVs expect and how they operate, this is just a very, very brief introduction. So obviously automated vehicles depend on multiple interconnected systems. For example, for environmental perception, they use LiDAR, camera, radar sensors, and for localization, GPS sensors, IMUs, and high-definition maps are commonly used. And these AVs can also have communication systems. That means using either 5G cellular network or some kind of vehicle-to-infrastructure communication system. So for the AVs to function safely and to operate them in rural area, all these interconnected systems must work reliably. But the problem is that in rural areas, like I said earlier, the assumptions may not work. So what's the role of this infrastructure in the AV performance? So for example, for perception tasks, usually lane markings are very critical, and road signs and road aids are also commonly used tasks that the perception handles. And localization, of course, that can be affected by the GPS quality, the map alignment, and available landmarks. And for communication, it requires a very good cellular coverage as well as data exchange. And there are challenges in all of these aspects when it comes to rural areas. So, for example, a lot of literature shows that lane markings are either faded or they're missing in most of the road segments. And road signs can be occluded, and there might be a very weak or even intermittent cellular coverage. And because of tall trees around the road, the localization might be affected, and etc. All of these are the challenge posed by rural roads. So obviously, this degraded infrastructure can have a very serious impact on the AV performance as it increases its uncertainty in making decisions. So the objective of this project is then to evaluate this rural roadway readiness for automated vehicles, and also to identify limitations that can affect the AV performance. So in the evaluation system, we included analyzing the several infrastructure components and also quantifying these components and also computing the overall readiness score. So those are the two main objectives of this project. So to get into the details of the framework, this is how we developed the evaluation framework. It has got four main components. The first one is selecting the infrastructure components for evaluation. So in our project, we considered physical and digital components. In the physical side, we took lane markings as one of the main components, and also traffic signs and pavement conditions are also considered. For digital side, we consider the connectivity, particularly the 5G connectivity, and also GPS accuracy, as well as high definition map availability. These are the selected infrastructure components for evaluation, and we pick this based on the literature, the assessment that we did with the literature. So the second component of the framework is preparing a measurement tool to analyze each of these components. So we used direct measurements using sensors, and we also used data-driven methods. For example, for visual perception components like lane detection, traffic sign detection, and pavement detection, we used deep learning-based models. And for connectivity measurement, we used a device for direct measurement of all the relevant information about the network. We also use data sets available out there just to make the evaluation more broad. For GPS, we also use direct measurements. And the third component of our framework is developing a scoring method for all of these components. That involves quantifying each of these components and defining a relative importance of each of these components, and then aggregating all these results to find one single result that tells us the readiness level of the infrastructure. And the last step is just automating the whole evaluation system. And that means with a software tool that simply takes raw data from the sensors and it applies the scoring method based on the framework. And then it generates a summary report. It also helps visualize the data and the evaluation result as well. So for the measurement tools, just to give you some more ideas about the measurement tools, for physical component, for example, for lane detection, we developed this segmentation model, and it has very good performance based on our benchmarking, and it has a very low false positive results. So we actually tested it with a real vehicle for lane keeping task, and we found very good performance. So we used it as a tool to measure lane markings. And for pavement detection, specifically for the pothole detection, we also developed a YOLO-based deep learning model. And its performance is on the low side because of lack of data set, and it has significant false positives. I'll explain this later. We did not really consider it for overall evaluation because of this. When it comes to traffic sign detection, again, a YOLO-based framework is used. And since there are no data sets for rural area traffic signs, and we created our own data set, and we found that the model works reasonably well. And for the digital component, GPS is directly measured. High definition map availability is like a yes or no decision. For connectivity, we use two approaches. One is direct measurement using this setup with the Raspberry Pi integrated with a 5G modem. And or for a broader evaluation, we also use the ocular dataset. It's an open dataset that everyone can access. And we consider the two approaches. So the scoring method, we've got the two components, the physical and the digital components. For the physical and digital components are individually evaluated first, and then they are combined using this the weighted average calculation. So we get the total score IT by combining these two components. So the weights for the digital and the physical components can be adjusted because they define the relative importance of these components. Getting into the details of each component, the physical component, like I said, we consider the three elements: the lane detection, the traffic sign detection, and the pavement detection. And again, because of some issues with the measuring, the tool that we developed for pavement detection, we did not really integrate it here. So we just relied on only the lane detection as a physical component. For the digital component side, we consider the three elements: connectivity, the GPS, and high definition maps. So they are combined this way. Again, W, the weight, the coefficients are the weights that we can use to adjust the relative importance of these elements. So lane detection, for the lane component, again, element, we consider that a lane is valid if it satisfies certain requirements. For example, if our model, or let's say the tool, detects significant lanes, as well as if it satisfies a minimum curvature requirement, it is considered valid, and we score it. We give it a score of 1. If only one valid lane boundary is detected, it will be scored as 0.5. Otherwise, we score it as 0. Similarly, for the digital components, the GPS, initially the errors are calculated based on the measurement. And if this error is below a certain threshold, in our case, 3 meters, we give the highest score. If this error is higher than 11 meters, we give it a very low score, like 0. Similarly, for the connectivity, we calculate the average upload-download speeds, and depending on the speed and the latency, we also calculate or score it based on this scoring mechanism. So for high-definition map, just score it as 1 if there is a high-definition map for that area. Otherwise, it gets 0. So overall, with these weights, we calculate the readiness level. If the total score is in this range, if it's above 0.8, it will be given as high score, high readiness. If it's below 0.4, it's low readiness. Otherwise, it's in the medium readiness range. So all these weights can be adjusted depending on the user. If someone wants to value one of the components better than the other, of course, these weights can be adjusted. So for this project, we've got 2 sites, and one is in North Carolina, Guilford County, the Brown Summit area, and the other one is in Georgia, Athens-Clarke counties. And for these 2 sites, we also have got 2 vehicle platforms. On the North Carolina side, we have a lab-developed automated driving system vehicle, and in the Georgia side, we used ADAS-equipped vehicles. So the North Carolina side, this is what the site looks like. This is actually one of the areas we considered. It's in the Brown Summit area. We drove around in other sides of the area as well. But for this presentation, we just picked this one. So this is almost 31-mile road. And these green flags show where we took the 5G measurement to verify whether the open data set available is correct or not. So this is our platform vehicle, the Lincoln MKZ, which is equipped with this camera at the top, and we have got GPS units under the trunk, and also the computing system as well as the 5G modems from 2 carriers. And this is what the result looks like. So for physical component, the lane marking assessment, this heat map shows that it has got a very good score. Actually, we got 0.97, which indicates high readiness if you consider only this component. And this is the per mile analysis. And as you can see, there are some segments where the lane score is low. And this happens in some of the intersections because the lane detection doesn't really work well when there is an intersection. And this is for the digital component, specifically for the GPS. In our test site, the GPS accuracy is very good in most places. In some road segments where there are tall trees, in our observation, the GPS accuracy can exceed, the error can exceed more than 3 meters. But generally, its accuracy is acceptable. It's very good. For high definition map, we don't have high definition map for this area, so its score is low, it's 0. And for the 5G connectivity, as you can see, this is based on the Ookla dataset, and we also verified it with our own measurement. The result is consistent. So as you can see, it's in the medium readiness level with a score of 0.6. So the average download upload speed is relatively acceptable for some tasks. Generally, the fluctuation is not, it's too high and it may not be that reliable. As you can see, in some spots, the upload or download speed is completely unavailable. There is no connection, in other words. It also shows, this is also the upload speed, which is average of 8 megabits per second. This is for download, 148 megabits per second, and the average latency is 27 milliseconds, which is reasonable. Of course, all these values might be okay for some AVs, but it may not be all acceptable for other AVs. It depends on the requirement. But overall, just based on our weighting, the connectivity score is relatively low, which is a 0.6 score. So the overall, combining all these components, we got 0.85, which is in the high range. And this is what the heat map shows. It's all green. So what we found based on this result, that if the AV is relying on visual perception plus simple navigation with GPS-based navigation, then the area is, I would say, ready based on this score. But depending on the requirement, the score can change. So to automate the whole evaluation process, we also developed the software tool that implements the framework. So it takes the synchronization data from the sensors and also considers the open data set. And it samples the data stream from the sensors. In our case, we sampled at 10 hertz. And based on the GPS coordinate, it also pulls statistical data about the network. And then it puts together, it scores them, and it provides the final result. And then it generates the report about the assessment. So that's what we achieved in the North Carolina site. And this is what the graphical user interface, the tool looks like. This is how we put the weights, and we provide the paths for the data. In this case, it takes a ROS robot operating system based data, which is a synchronized data. And different kind of data can also be provided. And this is what the dashboard looks like. So the dashboard simply shows the summary of the overall evaluation and the total distance covered and the generated report link, and also the per mile analysis and the score for each considered component. And on the right side, you'll get the evaluation result on the map. And there's key points all over the driven path, and it shows the individual scores for both digital and physical components. And if one wants to reweight the evaluation, of course, we also have this interest here, and the weights can be adjusted and re-evaluated to see what the score looks like depending on that specific requirement. So the second part will be presented by the Georgia side, Dr. Handong.
Sure. Thank you, Tesfamichael. Can you hear me?
Yes.
Okay, so let me see if I can share my screen. Oh, maybe not.
I
Can you?
can, yeah.
Yeah, please navigate the slides for me. Thank you. Okay, so for the UGA part, what we are doing is to focus on the ADAS vehicles, those production ADAS vehicles. And here we select two general platforms. One is the camera-based platform, that's the Toyota 4Runner. And another is the map-based ADAS platform, that's the Ford Mustang Mach-E. And then, because since those production AVs, we cannot directly get the sensing output from those vehicles, so we use the GPS unit and the dual GoPro camera to collect the two data. One is from the front view data, video data, and another is the dashboard view data to see where the vehicle responses to those traffic elements. And then the 5G performance data is based on the open source data. Next, please. So here is that's the test site. We selected a corridor from Athens Clarke County to Oconee County, and we have collected a total of 7 data segments, including daytime and nighttime test. Yeah, and this video here shows the example of the data collection, also the sign icon detection, the landmarking detection. So the big window is the front view video, and then the right corner window is the dashboard view video. Okay, next. So, but once we got all the raw video data or GPS data, that's based on the more about the video data. We use the AI methods to do the automatically data processing. So, especially for those front view video data, we did some similar things as the UNCAD. So we actually do the sign detection distance, but we also did distance estimation using PNP geometric method. And also we did a landmarking detection. But for the dashboard view, we use a sign icon detection with a self-trained YOLO, and then also a landmarking icon detection with a specialized binary threshold pipeline. Next, please. So for the evaluation framework here, we basically use the same, the readiness framework, but the difference here is based on the ADAS features. So for those production ADAS vehicles, what they can do is more about the landmarking, the stop sign, the speed limit sign. So we have 3 key index here for those 3 elements, and then we also have the digital index matrix. Next. And this table here shows, gives us the result regarding the landmarking detection. So here, one thing here is that both the map-based ADS and the camera-based ADS presented a median landmarking detection performance. And we also found that, the poor performance in segment 1 is likely because low driving speed on campuses, and that did not enable landmarking detection. And we also found that lighting has no significant impacts on landmarking detection. Next. So, and this table here shows the stop sign detection performance. And we found, well, really, one key thing here is the stop sign detection. One thing I want to mention here is that we compare the distance between the stop sign and the vehicle with the safe stopping distance. Okay, and then we found that the stop detection performance drops severely as speed limits increase, and the average stop sign index is just 0.33, underscoring a clear limitation of stop sign detection range for those ADAS vehicles. Yeah, next. And this one shows the speed limit sign detection performance. And we also found, for both of those ADS platforms, they are actually good, but the camera-based ADS is kind of lower than the map-based ADS. And also for segment 3 or 4 and 4, they are showing lower performance than others. That's probably due to poor speed limit sign condition like occlusion and the degraded visibility in those commercial areas. And still, the lighting has no significant impact on speed limit sign detection. Next. So here is a summary of all those, of all those index. For the physical infrastructure index, we figure out, for both of these two ADS platforms, they are just medium readiness. And we evaluate the digital infrastructure, the same, maybe a little bit better than, NC, the North Carolina, but still medium readiness. And then combine all these, these digital and the physical infrastructure, we figure out the overall readiness is still under 0.60. So that's the median readiness for those ADAS vehicles. Next.
Anything? Okay, you're already concluding.
Yeah, that's almost there. So to conclude everything, so here we develop a rural road infrastructure assessment that integrating physical and digital components, and we also use those data-driven tools for the measurements. And the key findings here is that we see strong performance in lane marking detection, the GPS positioning, and about for ADS perception, we see the performance is not only depends on the infrastructure conditions, but also based on the vehicle operating conditions. At the low operating speed won't enable the lane marking detection, and especially here for stop sign detection. Oh, wait a minute. So there is one key thing here is for stop sign detection, the ADS is are significantly shorter than the safe stopping distance recommended by AASHTO, and no HD map availability, and the 5G communication is limited. And the next, we want to talk about some limitations. So the neural network models here is is not very well tested for a large rural road network. And the second one is only a few infrastructure components are considered for readiness evaluation. And the third one is only a few AV models and types are tested. And the last one it's hard to estimate the cost and time for the whole evaluation. So if we can improve in the future, improve all the things, then probably later we can have a more comprehensive evaluation and then can scale this study to a larger network-wide deployment.
Great. Thank you so much. I think
And thanks, that's maybe the last one. We want to thank the CRC2C2 for all the support. And that's all. Thank you.
Thank you so much for both speakers. I know that the first with Dr. Sabi was having a hard stop at 1. If he's still around before he leaves, if there is any quick question to him before he leaves, and then we have more time for the second project. Is there any question to the first speaker before we go to the second project?
Yeah, I have a question.
Sure.
Okay, Dr. Sobi, you mentioned that you have dynamometer.
Yeah.
Yeah, dynamometer in the loop.
Yes.
So dynamometer is a physical system. So you're getting real signal, and then you have also getting signal from the simulation.
Yes.
There are two things. One is how do you merge the two, because the two are different, and the second one is there is a delay in the real system that you're getting from your physical system. Right. How do you handle this?
Yes, so that is in fact absolutely true, and that is what we wanted, right? Because if we have a purely software-based system, then those delays won't be there. The slip won't be there. The reaction between the tire and the rollers won't be there. So that is kind of why we want to have a physical system in the loop, so that we have a better idea of the dynamics. Now, as far as how that is done is, we can maybe have a longer discussion about that. Essentially, we have the system that we use is from a company called comma.ai. They sell these physical devices which are kind of for just general public, where they have the whole system packaged into this cell phone sized device with a camera in front and back, and you mount it on the windshield, and it looks at the outside using the camera, and it hijacks the signal that is running between the vehicle camera and the ECU, and it's essentially it just injects information into it, so it hijacks that signal. So we hijacked that comma.ai system and just ran the perception system, which is the super combo, on a laptop, created the images and the frames in Carla, and then used the comma.ai's hijacked pathway to inject our commands to the ECU. So that's how we kind of get the simulated environment into our system. And the rest of the things we do not really need to worry about, because that's just physical, as you said. The dynamometer is there. We just have to have information about the wheel speed and the the steering angle, essentially, and those can be directly read off from the CAN bus, because those informations are continuously produced anyway. So now if we have like an inverse kinematic model that takes the wheel speed and the steering angle and puts it through that inverse kinematic model, we have an idea of how the vehicle is moving forward, and then we can put that into the simulation. So that's how it is done.
Right. Thank you.
Great.
Thank you very much for that question.
Thank you so much. And I encourage the audience, if they do have follow-up questions with Dr. Sabib, feel free to email him. If you can leave your email on the chat box, and then feel free to leave. I know that you had a hard stop at 1 p.m.
Thank you so much.
Thank you so much.
Yes.
Yeah, we can continue a few more minutes if everybody else is available, and if the speakers for the second talks are available. So any questions for the second talk on digital and physical assessment of the infrastructure for rural roads? So if you have questions, feel free to send them. So
I had a quick question. I was wondering, like, especially the dashboards that you have prepared, it's really meaningful, especially with the publicly collected data set. Are you all planning to release it publicly, or kind of made accessible to for others to play around with it, or is it more internal?
Yeah, we're trying to make it available for everybody. But what we're going to make available is only the evaluated results.
Oh, okay.
And also maybe the weight adjustment, it should work without any neural network model behind it, because it's all about the initial evaluation is done with just the model, but at different threshold values. But after that, the weighting mechanism, I think it can be done offline without the model.
Yeah.
So we'll try to make it available for everybody. So,
no, I think that's a neat tech transfer usefulness. Yeah, thanks.
Yeah.
Great, thank you. So Dr. Jain, if you are asking a question, you're mute.
Okay, let me ask you a question. Since this is a collaborative effort, how much the distance impacted your collaboration?
Yeah, go ahead.
Okay, yeah. And I have to say, thanks for the collaboration. We actually learned a lot. At the beginning, we are just want to try some investigation with those physical infrastructure, but we also, based on this collaboration, we see a lot of, different things on those digital infrastructure, and we figure out that the digital infrastructure is still one limitation. Is still a limitation in Georgia, right? And also we learned a lot of, like the kind of we share the ideas of how to do those infrastructure detection, those landmarking detection, right? We share those models and we share the data sets. So that's kind of, help us to build maybe kind of a, decent or reasonable model for those evaluations. So yeah, I really want to thank the collaboration.
And I think at the end of the project, you ended up with two case studies, one in Georgia and then the other one in North Carolina, which was really valuable for the project. Great. Thank you.
Okay. Thank you, everyone. Thank you so much.
Thank you. Any other question before adjourning the meeting? It's already 1:06. One last questions, and then we're going to be wrapping up. Any last one question?